All right, so we've spent the last few days looking at many different types of primary energy sources. Today, we're going to turn our attention to electricity, which is a secondary energy source because it's produced by converting primary sources of energy, such as coal, natural gas, nuclear energy, solar energy, and wind energy, into electrical power. So let's think about it. Electricity is all around us, powering technology like our cell phones, computers, lights, soldering irons, and air conditioners. It's tough to escape in a modern world. Even when you try to escape electricity, it's still at work throughout nature, from the lightning in a thunderstorm to the synapses inside our body. But what exactly is electricity? Let's take a look. So, electricity is one of the most widely used forms of energy. Electricity is a form of energy that results from the flow of charged particles, including protons and electrons. Electrical energy can be transformed into many forms that are useful to us, such as light, heat, sound, and motion. Electrical energy has the ability to be converted, stored, transmitted, and reconverted efficiently into other forms of energy. And in case you didn't know, electricity travels at the speed of light, or more than 186,000 miles per second. Electricity has grown in technological leaps and bounds ever since 1752, when Benjamin Franklin flew a kite with a metal key tied to the string during a thunderstorm to prove that lightning was electric. Today, it's a necessary component to our fast-moving society. Take some time to watch this short video that discusses electricity. So you may be wondering how electricity is moved today. So it starts with transformers, which are electric devices that move electric energy from one set of circuits to another. They are used to efficiently transmit electricity over long distances. This makes it possible to supply electricity to homes and businesses located far from an electric generating plant. The electricity produced by a generator travels along cables to a transformer, which changes the electricity from low voltage to high voltage. Transmission lines are used to carry the electricity to a substation. Substations have transformers that change the high voltage electricity back into lower voltage electricity. From the substation, distribution lines carry the electricity to our homes and buildings that require low voltage electricity. So whenever I think of electricity as a kid, I always thought of lightning. And is it possible for us to harness that lightning to use as a potential energy source? Let's look at it. Lightning generates plenty of electricity. It starts as electrical charges developing inside a cloud. The positively and negatively charged atoms go to different parts of the cloud, the positive at the top, negative at the bottom. When the negatively charged atoms get too crowded, they jump to a different cloud or even to the ground. That jump causes a spark of static electricity called lightning. Even though lightning produces electricity, it is not practical to use that electricity for our power needs. There are too many obstacles. We don't know when or where lightning will strike, how powerful each bolt will be, or how to direct that surge of electricity into our electrical systems. What's more, the average lightning bolt produces about 270 kilowatt hours of electricity, but the average home uses 867 kilowatt hours of electricity every month. That means that one lightning bolt's energy could only power one home for about 9 days. You may have even wondered about static electricity. Have you ever reached with a metal doorknob and gotten shocked? That was static electricity at work. So let's consider how that happens. All matter is made up of atoms that contain protons, neutrons, and electrons. Protons have a positive charge, electrons have a negative charge, and neutrons have no charge. Atoms normally have the same number of protons and electrons, and in this state, the atom is considered neutral. However, by rubbing things together, you can make electrons move from one atom to another, causing atoms to have a positive or negative charge. This is known as static electricity. When you walk across a carpet, electrons move from the carpet to you, giving you extra electrons. Then, when you touch a doorknob, the electrons move from you to the knob, and you get that static electric shock. To better understand electricity, some basic information about atoms is super helpful. Atoms are the building blocks of the universe. Everything in the universe is made of atoms. Every star, every tree, and every animal. The human body is even made of atoms. Air and water are made of atoms too. Atoms are so small that millions of them would fit in the head of a pin. The center of an atom is called the nucleus. The nucleus is made up of particles called protons and neutrons. Protons have a positive charge. The number of protons in an atom determines the kind of atom or element it is. An element is a substance consisting of one type of atom. You might be familiar with the periodic table. The periodic table consists of elements with their atomic numbers, which is equivalent to the number of protons they have. For example, every atom of hydrogen has 1 proton and every atom of carbon has 6 protons. Neutrons carry no charge and their numbers can vary. If the nucleus was the size of a tennis ball, the atom would be the size of a sphere about 1,450 feet in diameter, or about the size of one of the largest sports stadiums in the world. Atoms are mostly empty space. If the naked eye could see an atom, it would look like a tiny cluster of balls surrounded by giant invisible bubbles or shells. The electrons would be on the surface of the bubbles, constantly spinning and moving to stay as far away from each other as possible. Electrons are held in their shells or electron orbitals by an electrical force while spinning around the nucleus. The outermost ring of electrons in an atom is referred to as valence electrons. The protons and electrons of an atom are attracted to each other. They both carry an electrical charge. Protons have a positive charge and electrons have the negative charge. The positive charge of the protons is equal to the negative charge of the electrons. Opposite charges attract each other. So an atom is in balance when it has an equal number of protons and electrons. For years, scientists have generated mathematical models to describe the structure of atoms, how particles interact, and how the structures of atoms give their physical properties. What they concluded is that the outermost ring, which contains the valence electrons, strongly influences an element's physical properties, such as whether they are a conductor or insulator of electricity. In this class, we will use the Bohr model to describe atoms. This model states that electrons travel in defined circular orbits around the nucleus at different energy levels. The orbits are labeled by an integer, the quantum number n. Electrons can jump from one orbit to another by emitting or absorbing energy. Electrons further from the nucleus are weakly held by the nucleus, and thus can be removed by spending less energy. Hence, we say they have higher energy. Decreased interaction with the nucleus is the principal reason why electrons further from the nucleus are higher in energy. Electrons usually remain a constant distance from the atom's nucleus in precise orbits. The orbit or shell closest to the nucleus can hold 2 electrons. The next orbit can hold up to 8. The outer orbits can even hold more. Therefore, the electrons in the orbits closest to the nucleus have a strong force of attraction to the protons. Sometimes the electrons in an atom's outermost orbits do not have a strong force of attraction to the protons. These electrons can be pushed out of their orbits. Applying a force can make them shift from one atom to another. This shifting of electrons is what causes electricity. Each principal energy level or orbit number in the Bohr model can be broken down into sublevels. These sublevels are not shown in this image above. Some of these sublevels are described as overlapping. Because of these overlapping sublevels in the Bohr model, the outside or valence orbit never has more than 8 electrons. The energy required to allow this electron to escape the valence shell and become free depends on the number of electrons in the valence shell. The valence shell of an atom can contain up to 8 electrons. Since copper only has 1 valence electron, freedom is easy. A slight voltage force will free it. The conductivity of the atom depends on the number of electrons that are in the valence shell. When an atom has only 1 electron in a valence shell, it's almost a perfect conductor. When an atom has 8 valence electrons, the valence shell is said to be complete, and the atom is an insulator. Therefore, conductivity decreases with an increase in the number of valence electrons. Since there are 6 valence electrons in sulfur, this is considered a good insulator. In electron flow, an electron from one orbit can knock out an electron from another orbit. When an atom loses an electron, it seeks another to fill its vacancy. And you can see here in this demonstration, electricity is created as electrons collide and transfer from one atom to the next. So to do a quick summary between conductors and insulators, We saw that conductors allow electrons to flow easily between atoms because there are only 1 to 3 valence electrons in its outermost orbit. Good examples of conductors include silver, copper, gold, and aluminum. On the other end, insulators make electron flow difficult between atoms because there are 5 to 8 valence electrons already filled in its outermost orbit. Good examples of insulators include plastic, glass, and rubber. And in case you were wondering, semiconductors have 4 valence electrons. A semiconductor, such as silicon or germanium, is a material whose resistance is halfway between that of a good conductor and a good insulator. Hence the name semiconductor. It's neither a good conductor or a good insulator. Electricity must have a complete path or electrical circuit before the electrons can move. Electrical circuits are made of several parts: an energy source to provide voltage, conductors to allow current to travel, insulators to limit that current's travel, and a load. Electrical circuits provide an uninterrupted path for current travel in 2 distinct categories of design: series circuits and parallel circuits. We will discuss both of these later on in our presentation. Electrons transmit an electrical charge through solid matter to produce an electric current. The number of electrons moving in electrical current is called amperage, or current measured in amps. The pressure pushing the electrons is voltage, measured in volts, and resistance is a material's tendency to resist the flow of charge. We will denote voltage by the capital letter V, current by the capital letter A, and resistance using the Greek letter omega. Understanding the relationship between current, voltage, and resistance will allow engineers to design efficient, safe, and functional electrical circuits. To better understand how the properties of electrical energy affect electricity, we will look at a water system to serve as a comparison to an electrical system. Consider our source of energy, a battery, as the water tank. The number of electrons moving or flowing in an electrical circuit is called current, and again is measured in amps. So when the faucet switch is off, is there any flow, or is there any current? No. But what about when the faucet switch is turned on? Is there any current or flow? Yes. Since electricity must have a complete or closed path before the electrons can move, the switch or on-off button on all electrical devices closes, which turns on, or opens, turns off an electrical circuit in the device. Turning or switching off a light opens a circuit and electrons cannot flow through the light. Turning a light on closes the circuit, which allows electricity to flow from one electric wire through the light bulb and then through the next wire. Referring back to our water example, the higher the water tank is above the outlet, the greater the pressure of the water. Using our battery as our source of energy provides voltage, which is forced pressure that causes the current of electric charge to flow. Therefore, in a linear circuit of fixed resistance, if we increase the voltage, the current will go up. And similarly, if we decrease the voltage, the current will go down. So when the faucet switch is off, is there any pressure? Yes, because there is pressure or voltage pushing against the pipe or tank and faucet. How about if the faucet switch is on? Is there any pressure? Yes, again, because there is pressure pushing current through the system. So it's important to note that voltage can exist across a circuit without current, but current cannot exist without voltage. So again, the battery provides the voltage that will push current through the bulb when the switch is on. When the switch is off, the voltage still remains. Resistance is the opposition to current flow. It is measured in ohms and is denoted using the Greek letter omega. So in our water scenario, what happens to the flow or current if we have resistance caused by a rock getting lodged in the pipe? Well, the flow or current decreases. So to generalize this, if we increase the resistance, the current goes down for a given voltage, and if we decrease the resistance, the current will go up. All materials have resistance. Conductors have a little resistance. Insulators provide a lot of resistance. Some electronic components, or resistors, have specific resistances. These are often needed to reduce current in order to protect other components or to adjust the amount of current that goes through other components. As we add resistance, The electrons do not flow freely through the circuit as the material they move through creates a restriction to the electron flow. In this example, the light bulb is providing some resistance when it's lit. Generally, in circuit diagrams, the flow of current through the circuit usually has an arrow to indicate the actual direction of the current flow. However, this usually indicates the direction of conventional current flow and is not necessarily the direction of the actual flow. Conventionally, this is the flow of positive charge around a circuit being positive to negative. The first diagram above shows the movement of the positive charge around a closed circuit flowing from the positive terminal of the battery through the circuit and returns to the negative terminal of the battery. This flow of current from positive to negative is generally known as conventional current flow. This was the convention chosen during the discovery of electricity, in which the direction of electric current was thought to flow in a circuit. It turns out, though, that the actual flow of electrons around a circuit is opposite to this direction of conventional current flow. The actual current flowing in an electrical circuit is composed of electrons that flow from the negative pole of the battery, which is the cathode, and return back to the positive pole, which is the anode of the battery. This is because the charge of an electron is negative by definition and so is attracted to the positive terminal. This flow of electrons is called electron flow. It makes no difference which way the current is flowing around the circuit as long as the direction is used consistently. The direction of current flow does not affect what the current does within the circuit. Generally, it is much easier to understand the conventional current flow from positive to negative. Both conventional current flow and electron flow are used in many professional industries. In general, the science disciplines tend to use electron flow, where the engineering disciplines use the conventional current flow. Since this is an engineering course, we will stick to using this conventional current flow. A multimeter is an instrument used to measure the properties of an electrical circuit, including finding the voltage, current, and resistance. It is sometimes referred to as the Swiss Army knife of electricity, as it can do so many different measurements. A basic multimeter has three parts: a display, a selection dial, and ports for the red and black probes. Every multimeter uses a red probe for positive and a black probe for negative. In order to measure voltage using a multimeter, you need to turn the selection dial to the voltage position, select the proper voltage range, and use the red and black probes to measure across a particular component. Note that the positive and negative signs represent polarity and flow. Thus, a digital multimeter will simply give a negative reading if the positive and negative terminals are reversed. The voltage reading can be different between any measured component. To measure current using a multimeter, turn the selection dial to the current position and select the proper amps range. In order to accurately read the current, you must break the circuit by removing one of the wires and connecting the red and black probes directly into the circuit's path of travel. That way, the current is going through two components by traveling straight through the multimeter. In order to measure resistance using a multimeter, start by turning off the power supply or removing it from the circuit. Next, turn the selection dial to the resistance position, select the proper resistance range, and use the red and black probes to measure across a particular component, similar to what you did for when you measured voltage. Ohm's law is a very simple and useful tool for analyzing electric circuits. It shows a mathematical relationship between current, voltage, and resistance, in which voltage is equal to the product of the current times the resistance. Specifically, the formula is V equals I times R. Based on this formula, current in a resistor varies in direct proportion to the voltage applied to it, and inversely proportional to the resistor's value. In other words, if you increase the voltage through a circuit whose resistance is fixed, the current goes up. If you decrease the voltage, the current goes down. If you double the voltage across a circuit, the current will also double. However, if the resistance is doubled, the current will fall by half. To take a look at an example that applies Ohm's law, we have a flashlight shown using a 6-volt battery and a bulb that has a resistance of 150 ohms. When the flashlight is on, how much current will be drawn from the battery? To describe this problem in detail, a schematic diagram was provided for you. We know that to calculate current, we could apply Ohm's law, which is V equals I times R. Since I'm trying to find current, I can manipulate this formula to get I by itself by dividing both sides by R. So we get I equals V over R. So I have 6 volts divided by 150 ohms, which gives me 0.04 amps, which is equivalent to 40 milliamps. To do this conversion, we'll look at the next slide. When completing calculations involving electrical circuits, you'll need to become familiar with a variety of unit conversions. The ones you need to know for this class have been organized for when dealing with numbers less than 1 or greater than 1. In the left-hand column for numbers less than 1, you'll rewrite using certain prefixes. Milli, denoted by the lowercase letter m, represents 10 to the negative third, or micro, denoted by the lowercase letter u, represents 10 to the negative 6. In the right column for numbers greater than 1, you'll rewrite using the prefixes kilo to denote the lowercase letter k, which represents 10 to the third, or mega, denoted by the uppercase letter m, which represents 10 to the power of 6. So if we look at the example from our last slide, we had an answer of 40 milliamps. This number is smaller than 1 because it uses milli, and to get its decimal equivalency, we need to move the decimal to the left. In this case, for milli, we're going to move it 3 times to the left. So 40 would be 1, 2, 3, which is going to be equivalent to 0.040 amps. And just to remain consistent, in tonight's homework, when you do your circuit calculations, I would prefer that all of your answers are left in terms of volts, amps, or ohms. As I mentioned before, components in a circuit can be connected in one of 2 ways, in series or in parallel. Here's an overview of series and parallel component configurations. In a series circuit, components are connected end to end, and there is only one single path for current to flow. In a parallel circuit, both ends of the components are connected together, and there are multiple paths for that current to flow. There are 2 important laws known as the Kirchhoff's laws that you will need to know when doing certain circuit calculations. Kirchhoff's voltage law, or KVL, states that the sum of all voltage drops in a series circuit equals the total applied voltage. A voltage drop is the amount the voltage lowers when crossing a component from the negative side to the positive side in a series circuit. If you placed a multimeter across a resistor, the voltage drops would be the amount of voltage you are reading. In Kirchhoff's current law, or KCL, states that the total current in a parallel circuit equals the sum of the individual branches of currents. Here we have a series circuit. Since there's only one path for current to flow in a series circuit, if the path is open anywhere in the circuit, the current stops flowing to all components and the light bulb would therefore not be lit. Here are some big characteristics of series circuits. First, the current flowing through every series component is always equal. The total resistance, or R subscript T, is equal to the sum of all the resistances. So if there was 3 resistances, my total resistance would be R1 plus R2 plus R3. The sum of all voltage drops, voltage 1 plus voltage 2 plus voltage 3, is equal to the total applied voltage. This is known as Kirchhoff's voltage law. At this point, I want you to pause the presentation and try working through the following example. The solution is found on the next 3 slides. Here we have a series circuit. Use the laws of circuit theory to calculate the following. I want you to find the total resistance, the current flowing through each component, the voltage across each component, and use the results to verify Kirchhoff's voltage law. So we have a schematic diagram listed below for you. We see that the total voltage is 12 volts. We have a resistance of 220 ohms. We have a second resistance of 470 ohms. And we have a third resistance of 1.2 kilo ohms. To find our total resistance, we'll simply add each of the resistances up together. So we had 220 ohms, 470 ohms, and 1.2 kilo ohms. We'll need to convert the 1.2 kilo ohms to just ohms. Since 1.2 kilo ohms is bigger than 1, we need to move our decimal place to the right 3 times for kilo. So 1.2 kilo ohms is equivalent to 1200 ohms. I just simply moved the decimal place 3 times to the right. So now I have 220 ohms plus 470 ohms plus 1200 ohms, which gives me 1900 ohms or 1.9 kilo ohms. Again, I would prefer for your answer to be listed in terms of ohms. So 1900 ohms is what I'm looking for. Next, I need to find the current flowing through each component. Since this is a series circuit, the current's the same throughout. So I can find the total current by using Ohm's law by taking the total voltage, dividing it by my total resistance. So I had 12 volts and I'm dividing it by 1.89 or 1.9 kilo ohms, which gives me 6.3 milliamps. Again, I don't want your answer in terms of milliamps, so I'm going to convert this by moving the decimal place 3 times to the left. So 6.3 would become 0.0063 amps. And since in a series circuit the current's the same throughout, we know that the current at each component is going to be exactly 6.3 milliamps or 0.0063 amps. In order to find the voltage across each component, I'll apply Ohm's law. To calculate voltage, we take the current multiplied by the resistance. So to find my first voltage, I'm going to take the current multiplied by the first resistance. So our current we found was 0.0063 amps. I'm going to times that by 220 ohms, and that will give me approximately 1.4 volts. In my second voltage, I'll take my current again, which should be the same, because this is a series circuit. So 0.0063 amps times it by my second resistance, which was 470 ohms, and that will give me 2.9 volts. In my third voltage, I'll take my current again, multiply it by the third resistance. So we have 0.0063 amps times that by 1200 ohms, and that will give me 7.6 volts. So if I want to verify Kirchhoff's voltage law, I'll take the voltage across each component, and it needs to equal my total voltage. So we can see when we added these up, we got 12 volts, which was equivalent to what we had as our total voltage. So this would verify Kirchhoff's voltage law. Now in a parallel circuit, there's more than one path for the current to flow. Therefore, if a component is removed, then it's possible for the current to take another path to reach other components. When lights are attached in parallel, each light is on its own circuit to the power source. If one filament burns out, it has no effect on the remaining lights, as they continue to be in a closed circuit with the power source. You can often see this when we're putting up Christmas lights. One light might go out, but the other ones still remain lit. So here are some key characteristics of parallel circuits. First, the voltage across every parallel component is equal. The total resistance is equal to the reciprocal of the sum of the reciprocals. So I like to think of this for finding total resistance. It's going to be 1 over the sum of the reciprocals across each resistance. And then we have that the sum of all the currents in each branch is equal to the total current. This is called Kirchhoff's current law. Again, I want you to pause this video and take a few minutes to try this next example involving parallel circuits. So for the parallel circuit shown below, use the laws of circuit theory to calculate the following: the total resistance, the voltage across each component, the current flowing through each component, and then use those results to verify Kirchhoff's current law. Again, a schematic diagram was given you guys to kind of give you the details of this problem. We're given that there's a total voltage of 15 volts. We have 3 branches in this parallel circuit. In the first branch, we have a resistance of 470 ohms. In the second branch, we have a resistance of 2.2 kilo ohms. And in the third branch, we have a resistance of 3.3 kilo ohms. Let's start by finding the total resistance, which is 1 over the sum of the reciprocals. So I'm going to do 1 over my first resistance, so 1 over 470 plus 1 over 2.2 kilo ohms, which is really 2,200 ohms, plus 1 over 3.3 kilo ohms, which is really 1 over 3,300 ohms. And then I'll do 1 over that answer. And if I do that, I get an answer of 350 ohms. Now, since this is a parallel circuit, we know that the voltage across each component in a parallel circuit is the same. Therefore, the voltage at the first component is equivalent to the voltage at the second component, which is equivalent to the voltage at the third component, which is equivalent to our total voltage, which is 15 volts. In order to calculate the current through each component, I'll again apply Ohm's law. To calculate current, we'll take the voltage and divide it by my resistance. So for my first current in the first branch, I'll take the voltage across the component and divide it by my first resistance. 15 volts divided by 470 ohms comes out to be 0.032 amps. To find my second current, I'll take the second voltage divided by the second resistance. 15 volts divided by 2,200 ohms, which will give me 0.0068 amps. To find my third current, I'll take the third voltage divided by the third resistance. 15 volts divided by 3,300 ohms, which gives me 4.5 milliamps, which is equivalent to 0.0045 amps. And then to find my total current, I'll take the total voltage divided by the total resistance. 15 volts divided by 476.6 ohms gives me 43 milliamps, or 0.043 amps. And then to verify Kirchhoff's current law, I need to show that the current at each branch is equivalent to the total current. Now, in this answer key, they did it in terms of milliamps. I, again, want you to use amps, so we'll just verify this using amps from the previous slide. So for our current at the first across the first branch, we had 0.032 amps, plus the current at the second branch was 0.0068 amps, plus the current across the third branch was 0.0045 amps, and if I add that up, I get my total current of 0.043. So this verifies Kirchhoff's current law. Here we have an example of a combination circuit, one that has both series and parallel arrangements. What would happen if you removed light 1? By removing light bulb 1, we now have an open circuit, therefore light bulbs 2 and 3 would be unlit. What about if I remove light bulb 2? Well, since there is more than one path for this current to travel, light bulb 1 would stay on, as well as light bulb 3. What if I remove light bulb 3? Well, in the same situation, light bulb 1 and light bulb 2 would still be on. And finally, when we're looking at electrical power, it's directly related to the amount of current and voltage within a system. To calculate power, we'll use the formula P equals IV. So power is equivalent to the current times the voltage, and the units that we'll use for power are measured in watts.